This is a little more graduated last year, so he asked me to come in for him. And I would like to say I'm a little sorry that I'm late because I couldn't find the building and the location of the classroom, so I got a little bit late here. And my name is Fadi. Yeah, that's like it's my family name. My first name is Bamba, but my family name is Fadi. Everyone calls me Fadi, so it's fine. Some people will think it's disrespectful, but it's totally fine where I'm from. Yeah, and I'm from the Gambia. I'm not sure if anyone here knows where is Gambia. Probably.
Yes.
Anyone?
Yes.
Oh yeah? Well, smart. Because like it's a very, very tiny country, so not a lot of people know about it. It's like less than 2 million people, and it's super far away from Taiwan. Okay, so the last week the professor told me that you guys are doing the shallow foundations, but you've started already, right? Doing shallow foundations with the professor. Do you remember where you stopped? I think you already finished the Tasagi's bearing capacity part. Okay, great. So hopefully today we can just move on to the next part, which is the Meyerhoff's bearing capacity and equations. Okay. But how about the previous ones, like the ones you did earlier, like the introduction for the shallow foundations and the Tazaki equations? Do you have any questions about those ones, or so far it's all good? All good, right? Okay, great. Do they have any homeworks on this? Oh, there's no homework. Oh, you'll get them homework. Okay, great. So, but before I go, I think I can ask a very quick question is that, while learning about shallow foundations, like, does any of you think about, why is it important for us to have foundation for our buildings? Maybe we can just put the building on the ground without any foundation. But why do we need foundations? Anyone think about that? Any idea? Yeah?
So the soil can bear the load, like if you just put it on top, we don't really spread the loads enough in the soil.
Exactly. So it's like all has to do with the bearing capacity, right? And also the settlement. It's like if you put the structure directly on the soil, when the structure gets into direct contact with the soil, it probably doesn't have enough strength to support the structure. So that's why usually the base of the foundation, we make it wider. The reason why we make it wider is to make sure that the loading is distributed in such a way that the soil underneath can actually handle the loading of the structure. So most of the time when we are doing the design for foundations, typically we will consider two things. We will consider the settlement and also the bearing capacity. Those are two of the most important things that we will consider. To a further extent, you may consider things like eccentricity, but bearing capacity and the settlement are the most important factors. Well, since we are dealing with shallow foundation, we're typically probably going to deal with ultimate bearing capacity, settlement, eccentricity, and then maybe, I'm not sure if you will do it in this class, but like how to actually design a foundation, like how to design a strip footing. When we talk about the other types of foundations, for example, the dip foundations, that's a lot more complicated. I remember in my undergraduate studies, we did not do that one. We only did shallow foundation. I'm not sure if this class will teach you how to use, how to do dip foundations, probably not. Because you can't even do the calculations with your hand. It's pretty complicated. Okay, so since you already talked about the Tazaki's bearing capacity problems, so today we just go to the Meyerhoff's bearing capacity equation. And here we can see we have the three failure zones, right? Like the one right underneath the foundation, the failure zone right underneath the foundation. But remember, that's the rigid zone, like the immediate zone. And then you have the zone 2, which is the rigid shear zone, and then the zone 3, which moves up, the continuous shear zone. Okay, so this foundation have a well-defined failure surface. And then here it says the angle from A to A. Oh, okay. This angle here, right? And the angle AA, well, here too, right? They are all assumed to be 45 plus phi over 2. And the phi over 2, the phi here should be the frictional angle, right? Is it? Yeah, that's the frictional angle. Okay, and then I think for the most part, the equations are actually quite similar. It's just that the factors that you take into consideration are quite different. So here we have like 3 different factors, right? NQ, NC, and N gamma. I know like when we're dealing with foundation problems, like the bearing capacity factors, we have some that have to do with the shape, right, of the foundation. That's the NS types. And then you also have the ones that have to do with the soil. And the third one, shape factors, soil factors, and inclination factors, exactly, that's the R. So here we have NQ, NC, and N gamma. And this problem is actually going to use the Meyerhoff's bearing capacity equation to solve the problem, and then it's an effective analysis. So when we talk about the effective analysis, for the most part, we are talking about the long-term condition of the foundation. Okay, for example, when it's short-term, probably you will not need the effective analysis because you still have the water. But long-term condition, the soil will get drained due to the loading on the foundation, on the soil. So you'll have the effective stress analysis. And then, but in that case, you'll see the equation is equal to C prime. So you have a value for this, C prime. And then the gamma you should use, yes, should also be prime. You should use the effective one. Because with time, these values will change. If you only consider the present condition, and then over time, if this value change, then probably the soil underneath may not be able to support the foundation anymore. So that's why it is important to consider the long-term condition of the foundation. And then the gamma, the unit weight also can be gamma prime due to the changes that they take over time. Okay, and the second condition is like the phi equal to 0, the frictional angle is 0. In this case, we are talking about the saturated clay in an undrained condition. So it's like a short-term problem. I don't know if the professor gave you an example. For example, sometimes when you're trying to find the frictional angle of sand, they will give you a very simple experiment. Like they give you sand and then you just point on this table and it may look something like this, like a little lump. But then if you're looking at the second condition, for example, the clay is saturated and then you try to point on this table, do you think you can have something like this? It's just going to be like this, right? So for the most part, that's why like the frictional angle for saturated clays, we just say take it to be 0. Okay, it's just phi equal to 0. So here, when you're using the Meyerhoff's bearing capacity equation, 2 things need to come to mind first. You need to know like, am I doing the effective stress analysis or am I doing the undrained or the short-term condition? Those 2 conditions are very important because otherwise you can use the wrong formulation. Okay? If you don't know whether you're dealing with 1 or 2, then maybe the whole procedure, whatever you do next, is probably wrong, it's not right. So the first thing is like that needs to be clear to you is that you need to understand, okay, what is the effective stress analysis? That is the long-term condition. And what is the undrained analysis or the short-term condition? Those are the 2 most important things. Once you figure those 2 out, then you can proceed to better understand like the formulations. Okay, so for the effective stress analysis, the long-term condition and the undrained condition, for example, the short-term. Do you have any questions about that? Any problems?
I have a question. How do you know what to choose in a real life, like in a real case?
That's a good question. Like for some problems, for the most part, they will do both analysis, like to see But in some cases, it would be a lot more ideal if you can use the long-term condition. Yeah. But if you want to be on the safe side, then how about you do both? And make sure that the foundation you are building is actually suitable in the short term and also the long term. But for example, if you are going to have a quiz or an examination, the teacher will probably specify, yeah, long term or short term, and you will go on from there. Okay, and it also gives us these values, right? So like the C will be Cu, that is the cohesion on drain, and the gamma now is gamma saturated. Instead of it being gamma prime for the long-term condition, right? It's now gamma saturated. That's the weight of the soil plus when it's having water, right? And you can now see that here you don't have these factors given, but here you already have them listed out for you, right? And there's a very simple reason why. In the on-drain condition, these factors are all exactly his values. By looking at here, can you make an assumption why these values are already given to you? Any?
The friction angle is 0.
Yeah, so it's like in this case, no matter what, your frictional angle is 0, right? So if the frictional angle is 0, that means by looking at our table, these values are exactly going to be this. But in this case, the frictional angle changes. It's different for different conditions. So you have to look at the table to be sure, like, what are the values for, let's say, N gamma, NQ, and NC, right? So basically, here those are the two most important things. And then you can see the equations already given here. So probably that in the exam they ask you to calculate the short-term condition, you just be like, thank God. Because you don't need to waste time to do the calculation for this. And if you are lucky enough, sometimes probably the professor or the TA might just give you a table at the back. So you can just look at the table instead of doing the calculations. And then, but I think the reason why sometimes they give you the equations is to make sure that you understand how the values come about. But actually in practice, like the engineers probably wouldn't want to waste their time doing this as well. They also just refer back to the table and make sure it is done as quickly as possible. Okay, so for the effective analysis and the on-drain condition, let's, okay, so you can see the values here. So it gives the values for the Meyerhoff's bearing capacity factors. So you can see why when phi equal to 0, the values exactly. And then they gave them up to phi equal to 60. That's a very strong soil. Okay. And oh yes. Okay. Okay, so here we have a table. We talk about the various factors. So these are some of the factors that we will consider, or that will be used in the equation when we are trying to calculate the, for example, the ultimate bearing capacity, and all the factors are given here. So number one is the shape factors, right? For it says if phi equal to 0, then if you want to calculate the FCF, then this is the equation, and then FQS and FYS, they are all equal, and FWS, they are all equal to 1. So in this case, you only need to calculate the FCS. And, but it changes. I think when we are dealing with solar foundations, the biggest problem is that you need to be able to follow like these procedures. Like, okay, am I dealing with a short-term problem? Am I dealing with a long-term problem? Okay, you decided that. Then you come here. Okay, the shape factors. Is the phi equal to 0? Is the phi greater than 0? Like all those things. It's like, and if you don't pay attention, you can easily make a mistake because you have a lot of formulations, right? So here it says if FCS, instead of being the one on top, is this, right? FQS equal to F gamma S, then the equation becomes this. So those 1, 2, 3, okay, like the cohesion, the gamma factor, and the QS, they are the shape factors. Those three can vary depending on the frictional angle. And then next you go to the depth factors. Okay, so this one depends on how deep the foundation is. Okay, so if, for example, if this is 0, then this is the equation you will use. And then here, I think you're all very familiar with that term already, right? The df should be the depth of the foundation, and this one is like the whatever. Okay, and then you have these two values which are equal to 1. But similarly, if this value is greater than 10, then now you have the equation like this. It changes with time. Okay, and finally, you also have the inclination factors. So sometimes maybe when you design the foundation, the loading is not actually coming straight through the middle of the foundation. Sometimes it's probably inclined. Okay, so you may also want to calculate the inclination factors. So the foundation itself is probably inclined. So these are also the equations that you will need for the inclination factors. And then you will realize that later on, we will typically use all these values when we want to calculate the ultimate bearing capacity. Okay, so here we just have an example. It says a rectangular footing is 2 by 4 in plan, situated on dry sand with an embedded depth of 1 meter. So the depth of embedment is 1 meter. Downward friction of sand is 32, and the unit weight of sand is 18. Okay, so if we have a problem like this and we want to solve it, what's the first thing we need to think? We need to ask ourselves. We already get all the parameters, right? But before you go on, what do you need to know? What's the first thing? Is it short term or is it long term, right? Or is it going to be on drain analysis or the drain analysis? Do you think we need to do an on-drain analysis for this? No, right? Because it's already dry sand. Okay, so it's pointless. It's already dry sand. So it's here, they are not telling you do an effective stress analysis, but they are indirectly telling you do an effective stress analysis by telling you it is dry sand. Okay? So if you look at this, you know, okay, I don't need to worry about the on-drain analysis. It is dry sand. Directly, you have only one problem, that is do the effective stress analysis. Okay, so we already have this very, very, very long equation that I hate to see when I was a student. And I hope in the exams you guys will give them these equations, right? I believe they will.
Professor asked it so many times that you need to must remember this.
You need to remember this equation?
CNC and Q and how come. Wow. So instead of this, they asked about the design.
Okay. Probably not this one, maybe the Tazaki, like the one that's a little shorter. If you need to remember this, just as the Taiwanese will say, simple, chiao. It's gonna be, yeah, but probably like this equation, you don't have to, I believe you don't have to remember, right? It's too long. Okay, so you can see here, you have all the various factors like CS, CD, CI, the inclination, the shape, the depth factor, and then also the shape, the depth, the inclination factor, and then also for gamma, for Q, the loading, and whatever, they're all like, and the cohesion, they're all given here, right? And then now, you have to find each of these individual factors for you to be able to find your QU, right? And then it says, for this sandy layer, the C equal to C prime. Okay, so, in some cases, when you only, for example, if the sand is not dry, the C is not necessarily equal to it's not, right? But in the dry condition, our C can be equal to C prime. Because when we think about it, when we say the drain condition, it means the water leaving the soil and then the characteristics of the soil changing, right? The gamma changing, the C prime changing. But if it is already dry, then there's no water leaving. So the C can be equal to the C prime. So when we are working with this problem, is the C equal to C prime and then whatever. And then in this case, it's equal to 0. For dry sand, the cohesion is equal to 0. So that's also something that you need to try to remember. Okay, and then by looking at the question, we know that the frictional angle or the angle of friction is 32. So we can use that 32 and go back to this table, okay? When we have 32, NC, NQ, and N gamma values are already given, so you list down those values here, right? And then you get the width of the foundation and the length 2 and 4, and then you can just directly substitute them in the equation above. Okay, so first and foremost, we want to calculate this, right? The FCS value, the FQS value, and then this and this and this. So if you are going to calculate these values, then you need to come back to where? Come back to this table, right? And then for here, we are going to use down here, right? Because the frictional angle is 32. Instead of using what is up, we are going to use here. And then the same thing here. Okay? And then this one for the inclination factor is already also the same. So in this problem, you may be wondering why do we use here, here, and not the ones up. But then if you look at the frictional angle, you can tell it's okay simply because the frictional angle is greater than 10. Okay, so once you have all these values, I think the problem is not that it is complicated. The problem is that it's quite long and a lot of minor calculations that you can easily make mistakes in. So it's like once you get all these factors, all these values, the only thing you need to do is just substitute them in here and then use your calculator to do the calculation. And then I think you can also save yourself the trouble. For example, maybe the factors like FCS, FCD, FCI, you probably don't need to calculate them anymore if you already know that this value is already 0, right? You can save yourself some time. Because at the end of the day, if you put them back there, it's still going to be 0. They are not essential. And I don't think any professor or TA will have a problem with that, right? You can just start it off. It's 0. I don't want to waste my time. And then just leave it to that. Okay, and then we have the gamma for the foundation. And then we just substitute all the other values. And then that's the final answer. I think this equation is quite straightforward and easy to understand. Does anyone have any equation, any question? Yes.
What is C equal to 0?
For dry sand, the cohesion is equal to 0 because it's like how attracted or how connected the particles are to each other. For example, if the soil particles are kind of wet or a little bit moist, or in clay, you will find out that they stick to each other. But for these dry sand particles, they have no sort of bonding within them. So the cohesion is like the force that is connecting them together. It's typically 0. It's like very non-existent. Sometimes if you are going to do some analysis, like the problem doesn't allow you to put it to 0, but maybe you may just put 1. But then that's what, like if you are using some numerical softwares and other tools. But if you are doing this type of analysis where you are just using your hand, you can just say phi equal to 0 and you're fine. Oh, sorry, C equal to 0.
Equation using 0 in the problem going to specify, right? Going to be a specified equation, right? Using 0.
Yeah, if it is 0, then you will give you the value. Yeah.
And what happens if the friction angle is between 0 and 10?
Between 0 and 10? Then we use greater than or equal to 10, frictional angle 0. I remember in most cases when it is between 0 to 10, we'll just use the one above. But for the most part, it's either 0 or greater than 10. Yes, greater than 10. It's very rare to see the frictional angle less than 10. For the most part, it's 0 or greater than 10. Yes.
I just wanted to mention, so every time it specifies that it's in dry conditions, we can assume that position is 0, or every time?
Yeah, for the dry soil sandy condition, then the condition, you can just say it's 0. That's one. Because if the sand is already very dry, you can tell there's no sort of interconnection or bonding between the particles. They are just separate particles. Okay? They are just separate particles. For example, you can just pick them up and then you can see when they are going down, they are just separate individual particles. So there's no sort of cohesion or no sort of interlocking between the particles. So that's why the cohesion is 0 in that case. Any more questions here? I think sometimes also by looking at it, it can also seem very, very simple, but for you to feel comfortable with it, you probably need to at least practice like 1 or 2 questions using each of these conditions. For example, the effective stress analysis and then the undrained short-term analysis. Then you can find out what is it that I don't understand, and then try to go back and then familiarize yourself with those points. But by looking at this, it actually can seem very, very easy, and then you probably never practice it, and then the day of the exam or whatever, you try to do it, you realize, oh, it's actually not that easy. It's like you can easily make mistakes. So please try to go over it and then solve this problem, or if you can get any other book, try to solve 1 or 2 problems for each of the problems, and then it will give you a much better understanding of this type of problems. Okay, if there is no question, we can just probably move on to the next one. I think that probably will be the ongoing condition. Why he doesn't? Oh, okay. Okay, so the next one we're gonna calculate the allowable load bearing capacity of a solar foundation. So we want to make sure that the loading from the foundation is actually acceptable, like the soil can actually sustain it, right? And then for the most part, when you're doing that, you need to apply a factor of safety to the ultimate bearing capacity. And the factor of safety depends on the design conditions. And for long-term conditions, usually the factor of safety should at least be equal to 3. Okay, should usually be 3 for the long-term condition. I mean, if you want to make it bigger, you can, but it depends on if your boss is willing to spend that much money. Okay, maybe the luckiest you can get them in long-term condition 3.1, 3.2. If you probably want to make it 5, maybe the next day you don't have a job. Okay, and it says 3 approaches for calculating the allowable bearing capacity. So in terms of the gross ultimate bearing capacity, so QU, which is the ultimate bearing capacity, right? The total loading you want to allow on the foundation divided by the factor of safety is equal to the Q allowable. I think this is quite reasonable. It's like if this is the maximum amount of load that this foundation can take, but you want to make sure that whatever load you are going to put on it is at least 3 times the size less than 3 times of this, then you just divide this by this value, right? The F, for example, 3, and then you get the Q allowable. And then now your Q bearing should be less than or equal to the Q allowable. That's the allowable loading on the soil, right? Why is it important for this to be less than or equal to this? Why is it important for the Q bearing to be less than or equal to the Q allowable?
Because otherwise the soil will fail.
Yes. So it's like if it is the reverse, that means the soil cannot sustain it, right? It's like the soil cannot sustain it. It's all about loading conditions. Like, okay, if it is this way, then it's enough. The soil will be strong enough to handle it. But if it is more than that, then it's the reverse. It cannot handle it, okay? And then this is also the second time, the number 2, it says, in terms of the net ultimate bearing capacity. So QU, they will give you the net. So, but this considers various things. It says the contribution of the soil charge is subtracted, okay? So QU equal to QU net, sorry. This one should be, yeah. Okay, so the Q ultimate, like the ultimate loading on the foundation, and this other Q, the soil charge. Do you have any idea what this Q is about? The soil charge loading. It's like for some conditions, like when you put the foundation on the soil will also be having some sort of loading underneath, like pushing it up. It's like, it's not only like you have the foundation pushing the soil down, but it's also have a soil charge loading that is trying to push up the foundation. So if you're trying to be more economical, then you can consider the soil charge loading, right? And then your Q net, that is the allowable ultimate bearing capacity. So you can just use that. So you just consider the contribution of the loading from underneath the foundation that is due to the soil. But in some cases, some people will think, okay, it will make my foundation more stable if I don't consider it, so I'll just only use this. But in some cases, they will try to subtract the soil charge loading from the soil. Okay, and then it's also still the same thing. So you can see that the allowable in all these cases is the ultimate divided by whatever factor of safety value that you want to have, right? Okay. Do we have any questions about these two formulations here? All good, right? Okay, great. Okay, so I think if time allows, we can I'll need to quickly go through this and then try to do something similar like we did previously. Okay, it says a rectangular footing is 2x4 in plan, situated on dry sand. Okay, seems like it's the same problem. Use the Melhoff bearing capacity equation. Okay, and then, so first we need to calculate this QU net. That's the allowable ultimate, the net bearing capacity, and then in terms of net ultimate bearing capacity, given that the footing is subjected to its total centric load of 300 on each space, so we also need to calculate the factor of safety of this foundation. So it says, according to example 3.3, the QU is this. Okay, so like the example we did earlier, the QU value we already get it, right? That is 1,031 kilonewton per meter squared. So you just put that back here. Instead of like redoing the whole equation, we just put that back here. And then next, you calculate the soil charge loading. And this is the equation you use if you want to calculate the soil charge loading. That's the gamma divided by, multiplied by the depth of the foundation. Gamma multiplied by df. Okay, so for example here, we know that the depth of the foundation is 1, right? And then the gamma is the unit weight is 18. So we easily can get this value, okay? The soil charge loading. And then now, the net bearing capacity will be like this, minus this, right? This minus this. And then you have that value over there.
What is 400?
Yeah, I'm trying to, where did it
It's-
come from?
It's 3,200 divided by 8. Because is Q divided by your.
Oh yes, yeah, so it's this, yeah, that value, right?
Yeah.
Divided by 8, and then we have this 400 and then minus here. Yes, so that's how this value can go up. Because we already have this value, QU. Okay, and once we have that, we just divide this QU net divided by the Q bearing capacity. So this part is just repeating here, right? This part is just repeating here. Okay, so I think everyone is also okay with how this one comes about, right? Okay, any more questions on this part? Okay, so once you get that, you get the QU net and the Q bearing capacity net, then you can just go on to estimate or evaluate the factor of safety for this type of problems. So for the most cases, in this type of problems, they will give you the vertical loading, vertical centric loading on the foundation. Then they will ask you to calculate the factor of safety. Or in some cases, you may be given the factor of safety and then probably ask you to calculate the loading on the foundation, something like that. Okay, and here another important thing is the centric loading. So that means the loading is through the center of the foundation, right? If it is not the case, the calculation will become a little bit more complicated. In that case, you have to consider eccentricity, right? Okay, we can see that so far all what we have done today, most of the problems all deal with they will specify that it's a dry sand, right? Dry sand or something like that, most of them. But in some situations, we will have groundwater. And then once you have groundwater, then you need some sort of modification to the equations that we have earlier. Now, the equations become a little bit more complicated. In some instances, you even have to do the calculation in different places, like above the groundwater and then below the groundwater level. So it's like we have different cases, different scenarios, like 3 different cases and scenarios when we are going to use the groundwater situation. I think 7 minutes. also have the class tomorrow, right? I think we probably don't have enough time to discuss the groundwater part like thoroughly. It may not be ideal to study right now. So if we possibly have any questions about the earlier parts or anything that is unclear, we can discuss about that. But if not, then the next part, which is the groundwater, we can do that tomorrow instead.
Can you go back to two slides?
Back?
Now where the factor of safety, work.
What is this one? This one.
The other one,
Is it this one?
37.
37, oh, sorry. That one, this one, right?
Here the QB is the bearing stress. So the Q allowable is the load bearing capacity, and it has to be greater or equal to the bearing stress, right? And that's when it's safe. So Q sub B is the bearing stress. And Q allowable is the bearing capacity.
Yes.
And QB is the stress, the bearing stress.
Yes. Oh, I get that, I get it. Yeah, Q, you mean this one? It's like allowable, right?
Yeah.
And then this one is the fair. Yeah. So for all this probably like, the U is just like ultimate, and then the AL is allowable, and then B is fair. So usually when we talk about the ultimate, it's like the maximum it can take, the maximum, and the allowable is like how much you want it to take. For example, most of the time, the factor of safety is equal to the ultimate divided by the allowable. For example, it can take like up to 300 kilonewtons, but in your design, you only want it to take about 100, because you want to have some factor of safety. So it's like always. Okay, if we have no other questions, we can stop here for today, and I'll see you all tomorrow.